is Dohoon from PSC team, and today I'm going to talk about lookup arguments and their implementations and the applications. At the end of the talk, Soowon will gonna share about the applications of these lookup arguments. Let me briefly explain about this lookup operation. So the lookup operation is just basically storing the value inside the pre-computed table and check whether some inputs are in the table. So this was mostly used for saving the cost of expensive computations inside the ZK circuits, for example, like bitwise operations. And it was also used for membership proof, for example, in semaphore protocol. So there is a concept called lookup singularity. So this is about lookup, of course. This was idea from Barry in PSC team. So the core of the lookup singularity is about that. So dealing with polynomials directly is very, very hard for the developers. And how about just pre-compute all the results of the execution in the table and just do only lookups inside the ZK circuit? So I think this was really nice idea because lookup arguments nicely encapsulates all complicated polynomial constraints. So at the time of starting to exploring this idea, the biggest obstacle was the proving time of the lookup arguments. So in order to achieve lookup singularity, so let's imagine that we want to achieve lookup singularity to prove the execution of the VM, then we should store all possible results of the execution into the table. And that would make the table size very, very large. So at the time of we explored this idea, we still could not handle large table efficiently. So, okay, let's see which lookup arguments were there at the time. So this is the line of works for the lookup arguments. So, of course, they are not all the lookup arguments that came out, but these are quite significant works that was introduced. And they all focus on to remove the dependency on the table size and to reduce the cost of the prover, which is, which linear is in the number of lookups. So, of course, these works were really great. But actually, the table independence comes from the pre-processing step, which takes quasi-linear time in the table size. And also, this still needs a larger roots of unity to encode the table inside the circuit. So if we want a very, very large table, then it's still quite infeasible. And actually, they are all still quasi-linear. They all require quasi-linear amount of field operations and the number of lookups. So our question was, how can we achieve sublinear or at least linear prover cost in the number of lookups? So these days, I was researching on this topic with many people. So we redefined our tools to design the new lookup IOP. So these four are the key hammers. So the first one is let's explore this lookup IOP inside the multivariate world rather than inside the univariate world. And the second was to use sum check protocol inside the multivariate setting. And there is a linear time sum check protocol which is very, very efficient for proving. And the third one is there was a nice tool called Spark Compiler to handle sparse multilinear polynomial that was introduced in Spartan paper, and the fourth was the GKR protocol. So let's see how we use this. So I'll show that how we developed the idea of new lookup IOP. So let's say let's model the lookup operation into this matrix vector multiplication. So this idea is not very surprising. This idea was just introduced in the Balu paper. And so here, the T is the public table, and A is the witness of the lookup, and M is the matrix that encodes the indices of our input inside the table. So M and A are just witness for lookup, and actually each row of M should be unit vector that contains only one non-zero element. So we tried to use sum check protocol to prove this relation. But the problem was, okay, sum check protocol is quite efficient, but at the last step of the sum check protocol, we should open these three multilinear polynomials. And for M and T, they have the size of the table, and we should open these two multilinear polynomials that have the size of the table at the random points. And if the table is very large, this is quite expensive in the term of proving cost. But actually, this matrix M is a very sparse matrix. So what the term sparse means that it has lots of zeros inside of it. Only few of them are non-zero elements, and all non-zero elements are just number 1. Because and we just figured out there is a nice tool to efficiently handle this kind of sparse multilinear polynomial that is called Spark compiler. So this Spark compiler uses offline memory checking technique and the GKR underneath, but I'll not go in depth here, but yeah, so it uses the hammers that we defined. But still, how about T? So T is the table, and if the T is very large, how to efficiently open this in the random points? So we were asking about this problem continuously, and then lasso just came out. So lasso is almost the same with our previous model, and lasso also uses Spark compiler to handle this sparse lookup matrix. And in addition to, lasso introduces new concept called decomposability of the lookup table. So decomposability of the lookup table is just can be expressed in this equation. So let's see what this means. So for example, let's imagine there is a 128 bits table, which is very, very large. And it is for ending two 64 bits elements. Then we can express that indexing into this very large table into indexing into these smaller subtables and then just combine them to obtain the original results. So this means that we can actually chunk the 64-bit elements into 8-bit chunks and then end them and then just recombine them to obtain the original results. So this idea was this idea that the table can be decomposed in this sense makes lasso more efficient, makes lasso a very efficient tool. So they uses the fact that if matrix M is sparse, then we can efficiently handle this. And also, if the table is decomposable, the T is very cheap to open. So actually, so the lasso achieves the proving cost that is almost linear in the number of lookups. So now we can re-ask that, does lasso really achieve lookup singularity? Yeah, so this is a just open question. I don't want to answer this in here, but yeah, let's just think about that and discuss this. Yeah. And besides that, there is another scheme called Lookup plus GKR. And yeah, this was based on the original Lookup arguments that is based on the logarithmic derivative trick, but it uses GKR protocol to avoid committing to some polynomials inside the Lookup scheme. So this makes Lookup much, much more cheaper in the term of proving cost. And it seems almost comparable with lasso in terms of the proving cost. So yeah, we should check whether lasso and Lookup plus GKR is really fast. So I just implemented it. Yeah. And I implemented lasso inside the hyperplonk system with plonkish arithmetization. You guys can just check this in this link. And hyperplonk is also based on the multivariate sum check protocol. So it was really nice to integrate lasso inside the hyperplonk. Yeah, thanks, Sam. Okay. And the main part of the implementation is this defining this decomposable table trait. So as I said, lasso requires the decomposable table. Developers should implement this decomposable table trait to use lasso lookup arguments. So my thoughts for this lasso implementation is that now the developers should think about the decomposability of the table, which seems at first quite tricky, but I think it is much easier to think about than thinking about the complicated polynomial constraints. But the concern was that it might not be fully backward compatible because as we now have to implement new decomposable table traits, then we just cannot simply drop in this new lookup argument inside the existing tooling, like such as Halo 2, and make everything much more faster. So we have to rewrite some codes, but yeah. So now I'm gonna share the benchmark results. So these are the candidates for the benchmarking lookup IOP. These five are, so the first one is the Halo 2 lookup argument, and the second one is univariate lookup. This was delivered from the geometry team called MV lookup, and the third one is multivariate lookup, and the fourth is lookup plus GKR and lasso. And these all tested with KZG polynomial commitment scheme in order to check exact performance of the lookup argument. And I used a circuit for benchmarking to range check 128 bits elements. So the strategy was just simple, just they decompose into 8 limbs of 16 bits for all other lookup arguments, and they all are in the same row because in order to reduce the effect to the proving time. And for lasso decomposable table, it also uses the same strategy. So this is the benchmark result. So it is benchmarked in terms of the proving time and the number of lookup queries. So you can see that Halo 2 lookup is the most slowest, and then MV lookup, and then lookup, and then lasso and lookup plus GKR is almost comparable each other. So, okay, let's say again. So lasso is almost 4 times faster than Halo 2 lookup argument, and almost 3 times faster than MV lookup, and almost 2 times faster than plain lookup. And lasso and lookup plus GKR was almost comparable each other. So this is my thoughts about this result. And yeah, so lasso and lookup plus GKR, they are almost comparable each other, and they are much more faster than Halo 2 lookup, which is very good. But still, they are not order of magnitude faster in our real implementation. So decomposability of lasso is really nice concept and very nice trick. But actually, we were already using this technique. Think about how we did range check inside the normal Halo 2 lookup arguments. We just decomposed them into the limbs and the range check into the smaller subtables. So we were already using some kind of this heuristic already. And lasso is quite formal generalization of this technique. Then just we can leverage this decomposability property of many tables, even if we do not use lasso. So I think the more important thing is the decomposability of the table. So yeah, and these are now the just future questions like, yeah, which one is the key for lookup singularity, or lasso or lookup plus GKR? Or can we achieve more efficient proving cost than them? Or are we in actual singularity in terms of the lookup argument? I mean, not the lookup singularity from Barry. I mean, are we all in the singularity of the cost in terms of the lookup argument? So I think these topics are really interesting to explore, and yeah, I want many others to explore. Yes, and yeah, this is my talk, and Soowon will gonna share about the application of this lookup argument.
Hello, I'm Soowon from PSC, and I will introduce Jolt, which is GKVM using Lasso and its implementation. So let's get back to lookup singularity again. So many people ask, why do we need more lookups? And I think it is quite a similar question as why don't we want to use polynomial constraint in the circuit? So I think the answer is there are several reasons for this. It's because polynomial constraints are not a paradigm that developers are used to, and it is hard to do traditional computation, as Dohoon mentioned before. So like, for example, like bitwise operation, and also it is very hard to do reasoning for the circuit. So if you want to do reasoning for the circuit, then you should solve the system of polynomialization. So, and by using like Gaussian elimination or Grabner basis for this. And also for that reason, it is hard to verify the circuit formally. So this lookup singularity idea is kind of making a new domain-specific language or tooling for a circuit. So all polynomial constraints are represented as lookups, and we can store all evaluation results of each operation, predefined operation to table like a cache. Then we can get the value from that table. So, but in this sense, then we should define fixed set for operation before proving or execution. So I think it seems very quite similar with the VM, because the VM has predefined set of instructions. So we can put VM structure to this kind of idea. So VM takes input and generates output, and it will make a proof from this own execution, like risk zero. And so we can use this approach to this lookup singularity idea. So for example, if you want to make GKVM for now, then you should use like existing library for circuit. Then you should write all the polynomial constraints on the circuit, and this GKVM will get the execution trace and output and as witnesses, and it will do some polynomial constraint checking. So, and then it will generate the proof. But if you have GKVM, then programmer can write a EVM on that GKVM, then it will generate proof itself. So we cannot, we don't have to write the circuit again. But the problem was the table size. So the tables are huge. So let's imagine that you want to make a ZKVM for some 64-bit architecture, then you should store 2 to the 128 values on the table for each instruction. So that is so big. So you should, at that time, so we should find a new lookup argument or an optimization technique for reducing the prover cost. So after that, Jolt came out with Lasso. So it is VM with lookup, and it is using RISC-V for instruction set, and it is using Lasso for lookup argument. And also, to use this Lasso, they proved that this subset of RISC-V is decomposable as well. And they're doing some trick for making a big table. So they are just putting combining all tables for the instruction into one table, and then they can avoid making very many tables for each instructions. So there are some building blocks of Jolt. So to prove the VM, then you should prove the correctness of memory operation and also the evaluations of instructions and also some remaining things to do in the circuit. So they used lasso for proving correctness of evaluations of instruction, and they used offline memory checking for proving correctness of all memory operations, and they used RNCS for proving correctness of some remaining things such as calculating program counter or and reducing some prover cost to put this field addition or multiplication, not just using lookup table and just rather than lookup table, then just put it into the RNCS, then it is very cheap because just one field addition and multiplication can replace it. So what I'm doing now is making Jolt for some small subset of RISC-V instruction set with edu. It is using small subset named RISC-U, and it's also using hyperplong, which is compatible with Halo 2 constraint system. So it is not complete, but yeah, we are doing making the composable table using a library which is implemented by Dohoon. And for the memory, then we are trying to figure out how to deal with this memory checking. But we have many options for like offline memory checking or memory consistency check, which is used in zkVM. And also, we can use Halo 2 for that system because we are using the Plonkish arithmetization for this multivariate setting. So we can write a circuit in the Halo 2 for field addition, multiplication, or calculating program counter in dynamic flow. So this is the plan for the next step. Yeah, thank you.
Yeah, thank you so much for introducing your implementation research. We have some minutes for the Q&A. So, okay.
So my question is for Dohoon. Initial implementation of Lasso by A16Z claimed it was like 40x faster or something like this, but you're observing like around 4x. So my question is, what is the reason of this divergence? Do you know any reasons why it doesn't actually cut it?
I'm sorry, Lev. Can you just repeat your question?
Yeah, okay. A16Z, they reported 40x advantage of Lasso compared to Halo 2 argument, but you're observing 4x. So there is that 10x factor hidden somewhere between their implementation and your implementation, and I'm wondering, where is it? Is it like different commitment scheme or what?
You mean why the result from A16Z and we are quite different because of the poly?
Yes. So do you know why they're different? Do you know the reason why they're so vastly different?
I'm not sure. I didn't dig into the A16Z's implementation, but I think we have to figure it out, of course, yeah.
Hey, thanks for your talk. I was wondering, in the lookup plus GKR approach, does it also have some constraints for the table? Like, do the tables need to be decomposable, or can it be used as a drop-in replacement for other lookup arguments?
Okay, so what is the point, sir?
I was wondering, you mentioned that in the case of Lasso, developers have to implement some trait, and it cannot just be used as a drop-in replacement for other lookup arguments. So I was wondering if that's also the case for the lookup approach.
Sorry, I think my ear is really bad.
Okay, I'll catch up with you.
Yeah, let's talk about it later, yeah.
Okay, thanks.
So, thanks for the talk. I was wondering, is there any better circuits to do the benchmarks over? such that you can abuse more the properties of lasso or, for example, lookup plus GKR. As for instance, in lookup plus GKR, what we tend to do with our Halo 2 lookup argument is to just move everything that we want to look up into a single column so that we pay less commitments in order to look up bytes or whatever it is, and we pay in copy constraints. But with lookup with GKR, what you can abuse is exactly that, because you just commit to the multiplicities. So you can have any amount of columns looking up into the same table, and it's not an issue. Indeed, it's more performant. So do you think that there's better circuits to benchmark such that maybe you can have more clear results on why something might be better than another one? Like, do you think this is the best choice for a circuit to get the benchmarks, or there's other things that can highlight much, much better results? This is in line with what Lev said.
Okay, so I'm not sure this is the best circuit for all. I mean, whether this is fair for all players in the lookup IOP for candidates, but so I think there can be another. So I almost try to make them fair by making all the limbs of decomposed limbs in the circuits that is in case of not lasso into the same row, not to affect the proving time that much. But I think also in original circuit, we have a table column as a fixed column, and we should commit to them. But in lasso, we do not have to commit to these kind of subtable polynomials. So I think that is one thing that makes difference too. So yeah, I think it can be some controversial result because I'm not sure whether this is 100% fair but yeah, I tried to, yeah. Thank you, yeah.
Right. Do you have any other questions or something else to add? Okay, great. Thank you so much, Soowon and Dohoon, for your presentation.